students, welcome back to another lecture in environmental modeling and simulation. Today I am going to walk you through MATLAB, which is a very popular software that is used for many different kinds of mathematical and modeling problems. And today our focus will be on using MATLAB for 1D systems. So far we have understood through qualitative approach how to understand some basic behavior of 1D systems, but if we want quantitative information, we fortunately have tools now on our hand to answer the quantitative problems. And MATLAB is a proprietary software, but it's also very commonly used. After MATLAB, I'll also walk you through how to do these analyses on open source software such as Octave and R. Octave is a corollary of MATLAB, though not as powerful usually. And Octave fans might disagree with me here. R, on the other hand, has been developed as a tool for statistical analyses and not as a tool for modeling and simulation. But it's a very versatile language. It's a very versatile platform. In this lecture, we are going to focus on MATLAB. So let's get started. Here you can see the screen of MATLAB Online, which is an option available for students of many different institutes across the globe. So if your institute subscribes to MATLAB, you may be able to log in on their website matlab.mathworks.com, and when you open up, you will see a screen that looks like this. Before you run a proper model or you save a script, you will see, before you write a script or run it, you will see that the screen resembles this, where the cursor sits at the place where you are supposed to write a script. We'll start with making a new script. Once you click on the new script option, the window splits into two different segments. The code will be run in the bottom segment, which is the command window, and the top segment is where we write our code. So let's say we want to start with a very simple one-dimensional model, which is dx by dt is equal to sine x. So there is an object that is whose velocity is varying following the sinusoidal function. Now, MATLAB offers us the option to completely integrate the system, especially for easily integratable system, we may not need it. But for systems that are slightly hard to integrate by hand, we can use MATLAB for integrating them. Even though this is not my favorite approach, I do want to demonstrate how to use MATLAB for integrating simple functions. First, in case you're not familiar with MATLAB syntax, I will take time to walk you through the syntax. First, you should know that the percentage sign denotes comment. So if you want to write comment, for example, first MATLAB command, and what we are going to do in this command is to integrate a simple 1D system. So let's start with the system dx by dt is equal to sine x. Just a note here on the using the percentage sign, MATLAB recognizes this sign as a sign for comment, which means that it will not run it as a command, the text that follows the line. For each line that is each line in the comment, you need another percentage sign. So for integrating the system, first you need to tell MATLAB that you are dealing with a system. So we'll do that by syms command. And we want to tell MATLAB that our system is yt, y is a variable, it's varying with time. And then we will inform MATLAB that this is an ODE, an ordinary differential equation that we are dealing with. And we know that because it's a differential system, we are telling MATLAB that it is a differential system. Now, notice here that MATLAB gives us recommendation on what might be the program we are trying to write. It's not always accurate. So it's very important for you to keep an eye and not make a mistake because you forgot to not accept a suggestion by MATLAB. So now here we used an equal sign. There are two kinds of equal sign, one which assigns a value and one which is actually used as an equal sign. Here we are assigning a value. To actually use as an equal sign, you need to put two equal signs, and our system is sine of y. Now, we need to give MATLAB initial condition. So let's say the initial condition is for y is equal to at time 0. So if you look here, in the first sentence of the code, we are defining the system as yt, which means the function is y and the information we'll be giving to calculate the value is that of time, which is an independent variable. So here when I say the condition is y0, automatically MATLAB understands that it is time that is equal to 0. So what is the value of y when time is equal to 0? Now because we are equating, we are showing the value of y at time t equal to 0, we'll use double equal signs. And let's say the value was 0.5. Now we are going to solve. So we are going to use a very simple MATLAB function, ySolve, and it will solve with t as independent time. Please be careful about the advice, the suggestions that MATLAB gives you. And we are going to use dsolve, which is our solver. ODE, we defined the ODE here. You notice as I typed ODE here, MATLAB highlighted ODE in the second line, which is actually the fifth line of the code. It recognizes that this particular string of characters has been used. Then we write the condition, and again, once I write the condition, MATLAB recognizes condition was defined in line 6. Now, this is sufficient for me to solve, so let's run it. To run, we just need to press the run. The MATLAB requires me to save this file before I run it, so let's call it lecture 9. Lecture 9.1. Okay, now notice here MATLAB is giving me an error saying that MATLAB names must start with a letter and contain only letters, numbers or underscores. However, instead of using an underscore, I used an hyphen. The wonderful thing about MATLAB is that if you make an error, and we will make errors intentionally to understand the messages, the error messages that MATLAB gives us. So here, MATLAB is telling me that it is running the code lecture 9_1. It is understanding what is the ODE function that I have given it. It also understands the initial value, and this is after integration what the function will look like. Y at any given time is given by this. Okay. Now let's try another function. We'll try a very simple function, let's say -2y. Now since this is the first time for some of us, some students here, first time getting exposed to MATLAB, I want to explain to you that if you cannot write 2y -2y, this is going to be confusing for MATLAB. If 2 and y, -2 and y are multiplied with each other, you have to put a multiplication sign, which is the asterisk. All right, the initial condition, we can change the initial condition or keep it as it is, and then we can ask MATLAB to integrate. So let's try it again. Once again, MATLAB tells us that it is running the code. It's running the code lecture 9.1, and it is integrating this particular differential function, and this is the initial condition, and after integrating, this is the answer it gets. Now, as you should understand by now in this course, I'm not very interested in integrating your differential equations and getting the integral and using that to understand how the system works, because even though you may have an integral available to you. So let's look at the integral of the first system, which was the sinusoidal wave. This is very hard to visualize. This is very hard to interpret unless you plot it, which I'll teach you how to do. But however, if we use geometric approach, or if we ask MATLAB in this particular case to not just give us an integral, but to actually find the values of the system in a given time interval for a given range of x, we can ask MATLAB to plot it for us. So that's what we are going to do now. Let's start a new code. So to start a new code, just press new here, and a new script file will open up for you. So now what we are going to do is we are going to ask MATLAB to help us solve our very first ordinary differential equation without integrating it. And let's start with logistic model. Now, since I'm starting with logistic model, it is very important for me to put a comment that says logistic model so that when I look back to my code, I know exactly what I was trying to model here. And I need to give initial values, but first let us write our system. Now, for logistic model, which is an which is an ordinary differential equation in one dimension, we are going to use a solver called ODE45. There are many different ordinary differential equation solvers in MATLAB. I am particularly fond of ODE45, and I'll tell you why. It uses fourth order RK method. Now, there are many different ways of using RK method. You can even do it by hand, which can be very laborious, or you can use Python or other languages like C to calculate using RK method. However, the beauty of ODE45, and I'll write it in as a comment, we will be using ODE45 solver. This is a solver that is inbuilt in MATLAB, so you do not, at least in case of MATLAB Online, you do not need to install it separately. And I believe that's also the case with standalone MATLAB. It has been a long time since I reinstalled my MATLAB. So from what I remember, it works. Now the beauty of ODE45 is that it has an adaptive step size capacity, which means at every step when it is doing the interpolation, extrapolation and trying to figure out what the next value should be, what the next step size should be, ODE45 can decide at every step what is the most appropriate step size in this particular step to minimize the error, to minimize the difference. So which makes ODE45 a very powerful solver. Another solver that is frequently used is called ODE23. And if you're interested in modeling, if you're interested in programming, I encourage you to explore ODE23 as well. ODE45 is what we are going to use here, as I find it more powerful. Alrighty, so the typical format of ODE45 looks like this. First, we write the output, what kind of output we are expecting from ODE45. We always write time first. So let's say time solution and then Y solution. Y here will be number of organisms that are growing following logistic growth model. Is equal to, so this is the output will be equal to the solution that will come from ODE45, and then here you have to tell what model you're talking about. So we are going to talk about a model by which will receive T and Y information, which is time and the value of Y, and then we write the name of the function. So let's write the name of function as first ODE, because it's the first ODE function that we are writing. And the input variables will be T and Y for this function. So we write that again. Then we need to give information about time. For what time limit are we solving this ordinary differential equation? And the time would be initial time and then the end time. When the time ends, we should not try to integrate or to get the solution for infinite time. And then we need to give initial values, which let's call it Y0. So this is the typical format. One way to understand what the format will be for any particular solver that you're using is to look up for help. So if you just type help 45 in the command window, the page that deals with the help section, the documentation section for OD45 will open up. And here's some information. It solves non-stiff differential equations, medium order method, and from t-span 1 to t-span n, which here is t0 to tn, with initial conditions y0, each row in the solution, and then it tells me more about OD45. What you need to know is the general format. So this is the general format of OD45. The output vector is ty, OD45 is a solver, this is the function you're referring to. This is the time limit and these are the initial condition, and then you can plot. Alrighty, now that we have read the basics of OD45 through the help, we can clear the screen. So to clear the screen, I like to use CLC, which will clear the whole screen. If you look at our the command, the code that I have written on the screen, there is a small red line here And be very careful. If you see these red lines, there's a very good chance that there is an error. I'm putting a semicolon here because I do not want to output every single iteration. So here I'll only get the output that I need. For that I put the semicolon. Now I need to define few things. First of all, I have not defined what t0, tn and y0 are. So let's do that. So let's say t0, which is our initial time, is actually 0. Yeah, and once again we'll put a semicolon. And then we want to define y0. So y0 is the initial number of organisms. They can't be 0. So let's say it is 4. We are starting, let's start with 1. Yeah, so 1 organism. And then we need to find out when is our time ending. So that is t end. Let's say time is 100 units of time. This is where our time is ending. And again, another semicolon. Now, this we need to plot results because t-sol and y-sol, the output here will give us a vector of solutions which will not make sense to us unless we plot them. So let's try plotting this. And to plot, first I'll write a comment here, plot results, so that when you look back at this, you know exactly what part of the code was responsible for plotting the results, which part of the code was responsible for writing the code for the solver. So what I want to plot is time versus number of organisms. So which would be t-sol, y-sol. It does not matter what you call t-sol, time. Sol is for solution, by the way. It does not have to be t-sol, it can be t, it can be time. You can use any string of characters for defining your variables. But what is important is the consistency. Also notice that for whatever information I have put so far, time always comes first and then comes your variable. This is a practice that is consistent throughout MATLAB. So always put time first and then put your variables. Okay. Now if I try to run this, I can tell you right away we'll get an error. But let's try to run this because then we'll learn about how to fix errors. Okay. So first it's asking me to save it. So let's save it as first. So it's running first and it is saying there is an error. So line 9, when calling a function or indexing a variable, use parentheses. So it is noticing that there is a mistake in parentheses somewhere here. There's also another mistake, which is that first ODE has not been defined. Okay, one mistake here is that between talking about the function and then defining the function, there should not be a comma. So let's remove that and then let's run it again. Alrighty, brilliant. Now it is saying that it does not understand, okay, here, unrecognized function or variable t1, also error in first ODE line 2. So first ODE, it does not understand first ODE, so we need to define a function first ODE. So let's do that. So you can start a new script, define your function ODE, first ODE and save it. The other method is to edit first ODE. Alright students, so we are going to run this code and see what error it gives us, and I'm expecting an error. I have noticed I have already removed the comma here because there should not be a comma between these two. But I'm expecting an error because we have not still defined first ODE, the function that needs to be run. Right now, there is no way for MATLAB to know that this is a logistic equation. So what we are going to do is we are going to define first ODE. So the typical method is to make a new script file, define function first ODE, and then run this code again. But we are going to try another method which I find much easier, is to use the command line, write the name of the file. As it does not exist, MATLAB will ask me to create it, and yes, I want to create another file called first ODE. So let's do one thing, let's clear the screen. And now what we are going to do is we are going to run this code and see what error it gives us. It says that it does not recognize a function or variable first ODE. So we are going to define a function first ODE. So to do that, start a new file here. So click on the new option. And now here we are going to define our function or first ODE. So we tell MATLAB what we are doing is we are defining a function. So type function dy. So we are dealing with different derivatives of y. And the name of the function will be first. In most command programming languages, the space can be optional around the equal sign, but using the space around the equal sign really makes the code look very tidy, so I recommend that. So now first ODE is the function we are defining. In the bracket, we will list the variables that will be input, t and y. Do not use semicolon here. On the next line, define dy, the function dy. So dy, we are talking about a logistic growth. So let's write a logistic growth here, 0.8 y minus 0.08 y square. Notice that I have not, I have used numbers instead of variables. You can also use constants like r instead of 0.8. But since this is the first time that we are covering MATLAB, let's look at the simple options here. Also remember, as I said earlier, you need to put an asterisk sign, the multiplication sign between the number and the variable. Okay, so this is our function that we have defined, and we need to save this function. So let's save this function, and the name of this function, let's say first ODE, because that's what it is for our class. Now we are going to go back. Now here, do not run this function. Instead, run here where we are asking the ODE solver to solve our function first ODE. MATLAB will know when it encounters first ODE that we need to look at the function first ODE defined here in the other file. So let's run now. So if you see here in the command window, for the MATLAB is giving me different values of dy at different steps that it has calculated, and then it has plotted that for this particular initial value, y0 is equal to 1. This is how the logistic growth will look like. Now we can alter, so notice here that the model that I have written, the carrying capacity is 10, which means 10 units of y. So if our initial starting number was 10, this plot will look different. Let's take a look. It will look like a straight line. Now if we start at a bigger number, let's start with 20. This is how our model will look, a fast decay followed by very slow approach towards the carrying capacity. So this was our first model that we ran using MATLAB. Now we are going to look at a very different situation. Notice here that I wanted the values of y for every single time between the given time interval starting from 0 to 100. Let's make it smaller to see the curves better. Yeah, not so dramatic now, is it? So MATLAB in its plot function has a lot of options. You can add labels on x-axis, y-axis, you can add title, and you can make your graphs using MATLAB publication worthy, but that is not the intention of this course, so I'm going to move ahead. But I want to give you an example where instead of having a continuous time, I'm only interested in solutions for fixed time interval or fixed time points. So let's start another model. So I'm going to press the new sign and I'm going to write the next model. And this model is for plug flow reactor. So first thing is we write the comment that this one is for plug flow reactor. And in plug flow reactor, we have a closed system which acts like a batch reactor, but it is a batch reactor in motion, which means basically we have an initial concentration of a contaminant or a compound that we are following. that compound either accumulates or decays within the closed confines of the plug flow of the plug, but the plug flows with time. So we have a velocity. So we have two things that we look at here. We look at the change in concentration and we look at the velocity of our plug. So our system will look something like this. We want VSol. Now, so I'm using the suffix sol to indicate solutions. Calling ODE45, telling it that we are going to be working with a system that uses V and C as its parameters. And then it's a plug flow reactor, so PFR, function, FUNC is for function. And then again the input variables are V and C, the velocity and the concentration of the contaminant or compound. The range of V would be V span and the initial concentration is C naught. If you compare this with the code we wrote here, the syntax is very similar. You write your solution matrix T sol, Y sol. In this case, our solution matrix is V sol, C sol. And then you call the ODE45, you tell them what function to take, write the span of the first independent variable, which is T. In this case, the independent variable is V, and then the initial value of Y, which in this case is the concentration. Now, once we have written this, we need to define things here like V span. What is your V span here? What is your C naught, initial concentration? So let's say our initial concentration is 1. We are going to put semicolon. Let's say our initial velocity is also, let's say our initial velocity is 0. And let's say we are interested at V end, so we are talking about specific velocities. In the case of logistic, it would be specific time intervals. So V end, we are looking at 3 distinct values. So notice here, when I did not put the equal sign and directly put the square bracket, MATLAB told me right away that there is a mistake here and I need to delete it. So let's say 1, 4, 8. And then I put a semicolon here. And then V span, which is the span of V, the velocity, is from V0 and V end. Perfect. MATLAB was correct here, guessing. Okay, and then we put a semicolon. So this is our code, and then we want MATLAB to plot this. Make sure that all the brackets are closed. Yep, looks good. So we want to plot, remember the independent variable will go first and then the other variable, C sol. Now if I run this, MATLAB will ask me about PFR FUNC function. Let's try. Okay, I need to save this. So let's call it second ODE. And when I run it, it says that it does not recognize the function, PFR function. So let's write a new function. And we'll call this function PFR function. So we are defining function here. So let us inform MATLAB that we are here to define a function. And our function is DC, which is the rate at which concentration of a compound or chemical is changing, is defined as PFR function, and the inputs are V and C. We do not use semicolon, and now we are going to write the function, which is DC is equal to. Now again, I have to make it easier. I'm not going to use constant characters for constant. I'm just going to write the constant here. So let's say this is our function, and then let's put a semicolon here. Let's save this function and let's call it PFR func, plug flow reactor function. Okay, we don't run this, we go to second ODE and we run this. Okay, now it's saying that at, okay, so notice here, I typed second ODE and it solved second ODE at the given time that I asked it to solve, which is 0, 1, 4, 8, because V span is from V0, which is 0, to Vn, which is 1, 4, 8. So it did not solve for all functions. However, there was an error in line 9. And this is amazing thing about MATLAB and similar software. They'll tell you exactly where the error is. It does not recognize the function or variable C as all, because notice here S is supposed to be capital and I used a small s. So let's run this again. And now notice that the line is not very smooth because I'm very particular about where I want the solution. I want it at 0, at 1, at 4 and 8. Students, this is all for today's class. In the next lecture, we will continue our discussion on MATLAB and then also talk about how we can eventually draw phase portraits. Alright students, this is all for today's lecture. In the next lecture, we'll continue with MATLAB and even explore two-dimensional systems, how we can solve 2D systems using MATLAB. However, since I have not covered 2D in the theory portion yet in this course, we will not be drawing phase portraits, but we will be looking into solving 2D models in MATLAB in the next lecture. See you there.